In this lesson, we're going to learn about the rate law. So we already know that concentration can impact reactants. So we know that if we increase the concentration of reactants, our rate is going to speed up. So it's going to increase. And if the concentration of reactants decreases, then our rate of reaction is going to be slower. The question is there a quantitative relationship? So do I have any numerical value that relates the concentration with the rate? So if we take a look at some data for this particular reaction, so N2O5 reacting to become 2NO2 and a half O2. So if we take a look at reaction data, in the first trial, the concentration of N2O5 initially, so this I here means the initial, and then remember square brackets around means concentration. So the initial concentration of N2O5 in the first trial was 0.45 moles per liter. And the rate of formation of oxygen was 2.7 times 10 to the negative 4 moles per liter per second. In the second trial, we had 0.90 as our initial concentration of N2O5. So in the second trial, there was twice as many moles per liter of the reactant, and we can see that the rate of reaction increased, and it was 5.4 times 10 to the negative 4. So here we had a doubling of the concentration, and 2.7 times 10 to the negative 4 times 2 is equal to 5.4 times 10 to the negative 4. In the third trial, the concentration initially of the reactant was 1.35 moles per liter, and the rate of formation was 8.2 times 10 to the negative 4. So this is 3 times greater than in the first trial. And if we take a look at the rate is also approximately 3 times greater. So 2.7 times 10 to the negative 4 times 3 is 8.1 times 10 to the negative 4, but with rounded numbers, so depending on the instrument we're using, that could impact that. So that's close enough that that is 3 times as great there. So here what we are seeing with the data in this particular experiment for this particular reaction is that when the reactant concentration is doubled, the rate of reaction also doubles. When the when the concentration of the reactant triples, the rate also triples. So what we have there is a direct relationship where whatever happens to the reactant concentration also happens to the rate. So if we compare, this just goes through that data. If we compare, so 0.9 divided by 0.45 is equal to 2, and the rates 5.4 times 10 to the negative 4 divided by 2.7 times 10 to the negative 4 is also 2. So, and then if we compare trials 1 and 3, there we see the tripling happening. So 1.35 is 3 times greater than 0.45, and the rate is also 3 times greater. So therefore, we have a proportional rate to concentration there. So if I take a look at another reaction, so carbon monoxide and nitrogen dioxide reacting to form carbon dioxide and nitrogen monoxide. So here is the reaction data, and this time I have 2 different reactants. And so sometimes increasing one reactant will not make a difference, but increasing another reactant will, and sometimes both of them will make a difference. So in the reaction data here, we have initial concentrations for both reactants. And when we look at the data, we have 2 trials with the same concentration of one reactant and 2 trials with the same concentration of the other reactant. And that is so when we compare, for example, trial 1 and 2, there is no change in the concentration of carbon monoxide, but there is a change in the concentration of nitrogen dioxide. So taking a look at this allows me to see the impact on the rate of just changing nitrogen dioxide. So keeping the concentration of carbon monoxide constant between these two trials means that any change in rate can only be attributed to the change in concentration of nitrogen dioxide. And then as we compare trials 1 and 3, the concentration of carbon monoxide has doubled, but the concentration of nitrogen dioxide here is constant. So that means that any change in rate is based only on the carbon monoxide concentration. So what we can do with the experimental data is we can determine specifically the impact that a certain change in concentration will have on the rate. So trials 1 and 2 compares the effect of the nitrogen dioxide concentration. So here we have a doubling happening, and from 5 times 10 to the negative 3 to 20 times 10 to the negative 3, what we have is a quadrupling happening. So when the rate of NO2, the concentration doubles, the rate quadruples. And when I look at carbon monoxide, so we have a doubling happening there. And when I look from here to here, there is no change happening. So the rate wasn't impacted by increasing the carbon monoxide concentration. So next few slides, just go through that. So trial 1 and 3, what we see is carbon monoxide. So this is the one where carbon monoxide doubled, but the rate stayed the same. So changing the carbon monoxide concentration had no impact on the rate. So what we do then is say there is some exponent here, and so 2 to some exponent is equal to 1. And the exponent that will give us an answer of 1, so 2 to the exponent 0, would give us an answer of 1 here. And this is going to become the exponent when we create a rate law, and we'll look at that momentarily. So what that means is that as the carbon monoxide concentration doubles, there is no change in the rate, and m equals 0, or an exponent of 0, would make this true. So that just means that the rate doesn't depend on the carbon monoxide concentration. So then with trial 1 and 2, there we saw as there was a doubling of the concentration of nitrogen dioxide, there was a quadrupling. So here we'll use a different exponent, so we'll use n here. And so 2 to some exponent n is equal to 4, and 2 squared is what that would be. So n is equal to 2 here. So as the concentration of nitrogen dioxide doubles, the rate quadruples, which means the rate here is proportional to the square of NO2. So here I'm going to end up squaring my concentration of NO2, and that will lead to the rate. So if I double the concentration, then 2 squared will then impact my rate. So in that case, quadrupling. So there is a quantitative relationship between the rate of reaction and the concentration, and what we have is called a rate law equation. So whatever our products are, this is going to be our stoichiometry. So I have a certain number of moles of reactant A and a certain number of moles of reactant B, and then I have the products. So the rate is equal to some rate constant K times the concentration of reactant A to the exponent m times the concentration of reactant B to the exponent n. So you can see here that our stoichiometry, so how many moles I need of each reactant, does not come into play in a rate equation. So K is a proportionality constant that is called the rate constant, and it does not have a specific set of units. The units depend on the exponents that we end up having in the rest of the equation. So K is temperature dependent, so my rate constant will change as the temperature changes. So if I heat something up, generally reactions are going to happen faster, and if I cool something down, the reaction happens slower. So K is temperature dependent, so even for the same reaction, a rate constant will be different at different temperatures. So it does have units, but the units are going to depend on the rest of the equation. So the larger the value of K is, the faster the reaction is going to proceed. So whatever we have with concentration of A to the exponent n and concentration of B to the exponent n, if we're multiplying that by a larger number, then our final answer is going to be a larger number. And the larger number we have for rate, the faster that reaction is happening. So M and N are the rate law exponents. Those do not change with temperature. So the rate constant will change, but the exponents do not. And those are referred to as the order of a reactant. And then we'll also have the overall order of a reaction. So generally we see 0, 1, or 2, but we can have other numbers as well, including fractions. The exponents are determined experimentally, so we just did that with a couple of examples of figuring out what the exponents would be, and it has nothing to do with stoichiometry, so nothing to do with the coefficients in a balanced equation. So A and B are the concentration of the reactants, and the values of the exponents are going to tell us the order of reaction. So we can determine based on M and N the order of each of the reactants, and then we can also add them up to get the overall order of reaction. So if we go back to that first example, we saw with N2O5 that we had a proportional relationship. So as there was a doubling of N2O5, there was a doubling of the rate, and as there was a tripling, there was a tripling. So if we had done exponents at that point, 2 to the m equals 2, so that is true when m equals 1. So in that case, our order of reaction would be, we would say that that is a first order reaction. Now in that particular example, there was only one reactant. So the order of our reactant is the same as the order of our reaction in that particular question. So the rate law that we would see for that is the rate is equal to K, some rate constant, times the concentration of N2O5. And because the exponent is 1, we don't have to write it in. So where that would show up is here, but exponents of 1, multiplications and divisions of 1, we don't write in. So we can actually calculate what that rate constant value is by substituting in some of the values from our chart. So the very first trial had a rate of 2.7 times 10 to the negative 4 moles per liters per second. And the concentration of N2O5 at that point was 0.45 moles per liter. So once I substitute those in, right now I have K times that concentration. So I can divide both sides by the concentration, 0.45 moles per liter, and that will isolate K and leave it on that side. So I can divide both sides by 0.5 moles per liter. So that's going to cancel here. And on this side, when I divide by 0.45 moles per liter, so I have moles per liter in the top and moles per liter in the bottom. And remember that it's moles per liter per second for the rate. So that second is actually in the denominator. So I can either write that as 1 over S or S to the negative 1. So my units for K for this particular reaction is equal to 0.00060 and units S to the negative 1, or per second, 1 over S. So then I can come back to my rate law and fill in the value for K that I've solved. So the rate for this particular reaction at the temperature that the experiment was performed at is equal to 0.00060 times the concentration of N2O5. So at this point, I could put in any concentration of N2O5, and as long as the temperature is the same as the reaction was originally performed at, I can calculate what the rate should be. So if we go back to example 2 with carbon monoxide and nitrogen dioxide, we figured out that carbon monoxide has no effect on the rate of reaction. So when we doubled carbon monoxide and left nitrogen dioxide the same, there was no change in the rate of reaction. And so there we had an exponent of 0. So carbon monoxide is said to be a 0 order reactant. With nitrogen dioxide, what we saw was when the concentration doubled, the rate quadrupled. So there the exponent was 2. And so nitrogen dioxide is a second order reactant. The overall order of the reaction is also second order because we add up our exponents. So in this case, we have 0 plus 2. And so because carbon monoxide was a 0 order and nitrogen dioxide is second order, here we have overall a second order reaction. So we can talk about the order of reaction of each reactant and also overall. So the rate law here then is the rate constant K times NO2 concentration squared. The carbon monoxide was 0 order, so anything to the exponent 0 is just 1. So we would only be multiplying this by 1, so we don't need to write that one in there. So CO does not show up in the rate law because it doesn't impact the rate. So once again, we can sub in values. So if we sub in a value for the concentration of NO2 and the resulting rate from the experimental data from before, we had 5 times 10 to the negative 3 moles per liter per second when the concentration of NO2 was 0.10 moles per liter. So we are going to square that amount according to our rate law. So what happens there is we square not only the number, but also the unit. So what I have here is 0.10 moles per liter squared, which means 0.10 moles per liter times 0.10 moles per liter, which means that I'm going to get an answer of 0.010 moles squared per liters squared. So I have moles times moles, and in the denominator I have liters times liters. So that is the value that I would divide on both sides. So it's going to cancel on this side as I move it over to here. So 0.010 moles squared per liters squared. So that means I'm going to get rid of a mole here and one of these ones, and get rid of one of the liters from there and one from there. So that means that I have 1 over S left on the top, and in the bottom I have mole per liter. So the easiest way to get rid of this is to change this division to a multiplication by using the reciprocal. And so then what I see is I have liters in the numerator, and in the denominator I have moles and seconds. So the units for this K value is liters per mole per second. So the K value here, the K constant or rate constant, is equal to 0.50 liters per mole per second. And so when I rewrite my rate law now with that constant in there, the rate for the reaction of carbon monoxide with nitrogen dioxide is equal to 0.50 times the concentration of NO2 squared. So we'll look at a new example here between nitrogen dioxide and fluorine gas. So there's the balanced equation. And we're being given that the rate is equal to K times concentration of NO2 to the exponent 1 times concentration of fluorine to the exponent 1. So both of these reactants are first order reactants, which means if I double the concentration, the rate doubles. And overall, it's a second order reaction. So if I were to double NO2 concentration and double the F2 concentration, then I would be doubling and doubling. So overall, the rate would quadruple. So that means that my overall order of reaction is 2. So each reactant, NO2 and F2, are each 1. And we can tell that by the exponents here. And the overall order, we add those together, and it's 2. So the reactants are each first order. Overall is second order. So if I were to double NO2 concentration, my rate would double. If I were to double the F2 concentration, my rate would double. So that means first order. If I were to double both of them, so when I look at the whole reaction now, if I double each of them, then it doubles once for the NO2 doubling and once for the F2 doubling. So that it is a second order reaction there. Okay, we'll look at one last example together. So if I have the reaction of 1,3-butadiene, and that is a second order reaction with respect to 1,3-butadiene. So if the initial rate of reaction is 32 millimoles per liter per minute at a particular initial concentration, what would be the initial rate if the initial concentration is C4H4? Now, one thing to clear up here, so we see the word initial showing up here and here and here. So when we talk about initial concentration and initial rate, if you remember when we looked at our rate graphs, I'm going to start at a certain concentration, and over time, that concentration of reactants is going to reduce because the reactants are getting used up. And as the concentration lowers, the rate changes as well because there are less reactants in the solution, and so then we have less collisions that are going to happen. So when we talk about our rates, our initial rate is based on our initial concentration, but as soon as the reaction starts, our concentration is no longer the same, and so our rate is also no longer the same. So even though we see initial rate of reaction and initial concentration, and then again an initial rate of reaction and initial concentration, what this is talking about is for a particular reaction, so we'll call this that reaction, the rate at the very beginning, so remember if I draw a tangent line to that point, the rate at that point is 32 millimoles per liter per minute. So the question is asking that if I have a different starting concentration, so if I were to double the concentration, what is going to happen to the initial rate? So what would be the rate at this point if I have a doubled concentration? So what I know from the question is that we have a second order reaction. So second order means that I have an exponent of 2. So it means that if I double the initial concentration, then I double and double again my rate of reaction. So here is the balanced equation for the reaction. Now this part, we're going to ignore this part because that's not how I would write this. So the initial rate of reaction, we were told, is second order. So we have some K constant, and whatever happens to our concentration, that is going to happen twice. So in this case, if what I'm doing is doubling it, so whatever that concentration was, we'll call it X. If I double that, then I'm going to end up doubling it twice because of the concentration. So instead of X, I'm now going to have 2X, and that's going to be squared. So that's where this 2 times 2 comes in. But what I would do is the rate was 32 millimoles. So if I double my concentration, the reaction is going to double and then double again because it's second order. So once and then twice because it's second order. So 32 times 2 times 2, or times 2 squared, or 4. So if the concentration is doubled, in this case, because we have a second order, the rate is quadrupled. So we had 32 millimoles per liters per minute. And so when we multiply that, we are going to get 128 millimoles, or 0.128, or once we put in our sig dig, 0.13 moles per liter per minute. So remember that we had millimoles here, and so we're ending with moles per liter per minute. So we had second order reaction, doubled our concentration, so that meant 2 squared, which is 4, so we're quadrupling the rate of reaction here.